Sorry, I had to start. I had forgotten to start the recording, so I now started it. Sorry.
Okay, let me just go. I have to take up my laser pointer and press continue, otherwise I cannot do it. But now I can do it. Great. So again, just very quickly, this is called quantum toric geometry, and this is in this talk I will present these 3 papers, especially the first. So if you are a beginner, I recommend the first, and then the second, that it has a lot of motivation, and only after the first to the third, that is all the technical details. And it's a long omnibus 100-page paper. But first you can look at 1 and 2 in order of motivation and complexity. In any case, again, it was very important the moment where Descartes unified algebra and geometry, the geometry of Euclid and the algebra of Al-Khwarizmi and Omar Khayyam got their unification in Descartes. So it was in the publication in 1637 of La Géométrie that this occurs. And well, we all know this is the so-called analytic geometry, or the beginnings of the algebraic geometry, in fact. So, of course, then Riemann comes in, and in 1857, he produces his masterpiece, where he now fully fledged founds modern algebraic geometry. And what is very natural now for us, that is to use the complex numbers, was revolutionary at the moment to do this geometry. And notice that when we move from the real numbers to the complex numbers, in this first step of generalization, we lose the order, of course. We still have a field, we still have all the other properties, but we lose the order. So then we move to 1858, and well, again, it seems like a different source of ideas to solve more and more classes of equations, and the evolution of concept of number comes from this desire to solve wider and wider classes of equations. And just as complex numbers arise from the need to solve quadratic equations and then cubic equations, matrices appear from the need to solve systems of linear equations with many variables. Matrices appear in the 9 chapters of the mathematical art, incredibly beautiful masterpiece, which I recommend. But really, they don't really come of age until 1850 to 1858. And finally, in a memoir on the theory of matrices by Cayley, it is understood that what we say today, they form a ring, and a non-commutative ring, a non-commutative algebra at that. And this is the first real important example of non-commutativity in mathematics. So when we move to complex numbers, we lose the order. And when we move to matrices, we lose commutativity. And well, this brings us to 1980. And in 1980, there is this Combe-Rendu note and made into a 1985 IHES paper, non-commutative differential geometry. And now the field of non-commutative geometry, that is to say, the study of spaces in a very, it might sound very puzzling at first, but they may or may not have points. They may have very few points, but the functions on this space, on these spaces, usually if you have a space, you can consider its algebra, its ring of functions. And of course, functions, you multiply them and they commute. But in these spaces, the main characteristic is that when you multiply functions, variables in local coordinates on these spaces, they don't quite commute. And this, of course, very related to quantum mechanics. You could think that these spaces have coordinate is valued in matrices rather than in the real numbers, in these generalized numbers, as Gelfand would have it. We backtrack a little bit and we move to 1925. And in 1925, there is this monumental, very important paper in physics about quantum mechanics 2. Born and Heisenberg win Nobel Prize for this. Jordan doesn't. And as I can read here, the main insight was Heisenberg's, and it is the stuff of legend. In order to escape an attack of hay fever on June 7th, 1925, Heisenberg leaves Göttingen for Helgoland, and between learning poems by Goethe and climbing, he realized that by positing non-commuting observables, he can solve the observational puzzle of the behavior of the spectral lines of hydrogen, as I will explain. After a sleepless night of calculation, he was so deeply shaken by the result that he left the house and awaited the sunrise on top of a rock. Heisenberg rapidly wrote a paper using this insight, but afraid of its own originality, he first asked Born to look at it. And it didn't take long for Born to realize that he could make sense of these dreams, of these intimations, in the language of matrices, making it more palatable for mathematical physicists and physicists at the time, and mathematicians. So that's the situation in 1925. And the situation is more or less the following. You have this prism, and you put the light taken from radiation emitted by hydrogen, and or any other element, and you decompose the light, and then you see these lines that is spectrum, and you measure its wavelengths or whatever. And such data, the list of wavelengths, is what is known as an atomic spectrum. For example, for the hydrogen atom, by performing such experiments, one gets this spectrum. This one. And L is certain number, is certain length, you know. And these are the wavelengths that you get for the spectrum of the hydrogen atom. And you get all these rational numbers. And then you look at the rational numbers very carefully. And you get, if you look at more elements and all this spectrum, and you start seeing a lot of rational numbers. And then, well, then you see that the spectrum for the hydrogen atom is like that. And that for more complicated, called hydrogenic, but anyways, more complicated atoms, it still looks like this. I'm omitting the square of the atomic number, and I'm erasing some constants to express the integer structure more clearly. And well, you get this for certain integer values, and M is fixed. And again, we obtain this discrete spectrum, and the discreteness of this spectrum is what throws us into the foundations, into the creation, into the discovery of quantum mechanics. So this is the notes from 1888 in the left. But then in the right, the discreteness of the spectrum contradicts classical mechanics. Because from classical mechanics, you would not predict this. You would predict this additive subgroup of the real line, and it's not what you get. What the experiments prescribe is the so-called Rydberg combination principle from 1908. And what this says is that there exists an abstract set. Just imagine an abstract set, I, j, k, etc., finite, that labels the frequencies such that the spectrum is the difference of some numbers that do not appear on the spectrum. Vi, Vj do not appear on the spectrum, but their difference do. And the Ritz-Rydberg combination principle states that this should be subindices, sorry, that Vik plus Vij is Vjk, that you have this, the spectrum wants to be a group as classical mechanics would have it, but it's not quite a group, or a groupoid, a groupoid. Let me explain this. The sum of certain frequencies when J equals L are allowed, but not Bij plus Blk, you can sometimes, and this indicates a groupoid structure. So what is the Heisenberg groupoid? Well, is this mathematical object that I present here. So I take just the labels for the frequencies and I put them on a set. And then I take I cross I, I cross I is going to be the groupoid. And I imagine that I cross I is just an arrow between I and J for the element I comma J. I imagine it to be an arrow xij between I and J. And so the source of this arrow is I, the target of this arrow is J, and this has this, I can multiply arrows, but only when J equals L. Ij and Lk can be multiplied. And then when you do that, you multiply them, then you get Ik. And then you get this multiplication structure on this set, but it's a partial multiplication. And so this thing becomes a groupoid and not a group. And a groupoid is one of the main building blocks in non-commutative geometry. So what is a groupoid? It's a type of category. And we will see that its convolution algebra is the non-commutative algebra we're looking for to understand the correct variables to do the mechanics, the quantum mechanics. So a category, most of you have seen it. I will very quickly say that it has objects and has arrows, and that the arrows goes from one object to another object. You can think of it as a sort of a graph, but with a structure, an algebraic structure. Because not only you have this graph of arrows between objects, you also have, from every object, you have an identity arrow from the object to itself, and you have a composition of arrows. And of course, only if the target of one arrow is the source of the other arrow, then you can compose them. And this is the multiplication structure. And so far, it's just data. But now there is some important properties. There is this associativity of the multiplication. This is the strong property in a category, the associativity of the multiplication of the arrows, and the identity for every element, for every object of the category. So a typical composition of two arrows looks like this, where A, B, C are objects of a category, and F and G are two arrows. Then you get the multiplication, the composition of these two arrows, and you get the identity arrows all around the place. So this is what a category is. And let me see how I'm doing with my time. Perfect. And then the archetypical example, of course, is the category of all sets, where the objects are all sets and the arrows are all mappings. This clearly satisfies all the properties that I requested. But then there is also these subcategories, also very large subcategories. For example, the category of all groups. Now, it's not all sets, they have to be groups. And of course, they are not all functions, they have to be group homomorphisms. And you still have a very good subcategory. And these are the archetypical examples of categories. But they are very large. I will be using small categories where the family of objects is a set and the family of arrows is a set. And moreover, I will ask that the family of objects is a manifold and the family of arrows is a manifold. And this will be called a Lie category. So anyway, category theory well, appears in 1945 in a classical paper in the Transactions, General Theory of Natural Equivalence by Eilenberg and MacLane. There they are. And they are very much under the influence of Emmy Noether to define this concept. So one could say that it's the three of them who find this, who isolate the idea of a category. Anyway, it's 1945, General Theory of Natural Equivalences, the year that the war ends. Category theory starts. Anyway, so that's the story. And well, groupoids are categories where every arrow, just like groups are monoids where every element has an inverse, groupoids are categories where every arrow has an inverse. And it is what you would expect. And every group is a groupoid. I mean, if you give me a group, I can form a category that has only one object and as many arrows as the element of the group. And this category that has only one object and as many arrows as the element of the group is a category, but it is a groupoid because G was a group. So this is the most typical example of a groupoid, but not every groupoid is a group. Every equivalence relation on the other extreme can be made into a groupoid. Now you have many objects. You have many objects. You have I objects. And now you have some arrows there, a subset of I cross I. You imagine them as arrows. And because of transitivity, you have a composition of the equivalence relation. And then you get a groupoid. And this is, if I is a set of frequencies on the spectrum, this is the Heisenberg groupoid, Heisenberg-Ritz-Rydberg groupoid. And these groupoids are going to be very important for us to find the correct algebra of observables in quantum mechanics. In any case, Lie groupoids are groupoids that the set of objects is a manifold and the set of arrows is a manifold. For example, the discrete one clearly are Lie groupoids, and the case I cross I from the Ritz-Rydberg combination principle tells me that the frequencies form a real valued groupoid representation of the groupoid for the saturated equivalence relation in the set of frequencies. And this implies that the space momentum coordinates in the microscopic phase space do not commute, as Heisenberg discovered. And they are really matrices, as I will explain very soon. In any case, that's an example of a groupoid. Lie groupoid is discrete, but it's a Lie groupoid. Another example of a Lie groupoid is a group action. A Lie group is a Lie groupoid, of course. A Lie group is a Lie groupoid. And a group action of a Lie group on a manifold is a Lie groupoid. Now the objects are the points of the manifolds, and the arrows are pairs of a point in the manifold and an element G. And there you have the composition formula, and then it satisfies all the axioms of a Lie groupoid. And all the source, target map, and identity, and etc. are C-infinity maps. Structural maps of the groupoid are C-infinity smooth mappings. In any case, well, a topological Lie groupoid is a small groupoid that manifolds, as I said. In any case, here we have étal is a condition that occurs in an atlas of a manifold. And what étal means is that S and T are local diffeomorphisms, the source and the target map of the groupoid from the manifold of arrows to the manifold of objects are local diffeomorphisms. And this occurs in an atlas of a manifold. To any atlas of a manifold, I can associate an étal groupoid. The objects are pairs Mi, where M is in UI. That are the objects of the groupoid, of the category, that is a groupoid. The arrows are triples Mij, where M is in UI intersection Ij. And the source of Mij is Mi, the target of Mij is Mj, and the composition of MJK with MIJ is MIK. And this forms a groupoid associated to every atlas of a manifold. So you have a Lie groupoid associated to every atlas of a manifold. And I very much recommend this book, my Murdyke Mergen or something like that. I'm sorry for the second name pronunciation. On these issues. In any case, just as spaces admit homotopy equivalence and then they have a homotopy theory, categories admit something called equivalence of categories. And I will not go very much into this, but this is a sort of homotopy equivalence of categories. It's not isomorphism, it's a homotopy equivalence of categories. And then there is an associated homotopy theory. But if you want it to be smooth, this homotopy equivalence of categories, of groupoids, you have to make this definition. So this definition has a lot of symbols, but what it means, you are to think of it as homotopy equivalence of groupoids in the right homotopy category. And this is what Morita equivalence is. In any case, a groupoid up to this Morita equivalence is what it's called a stack associated to the groupoid. The equivalence class of a groupoid up to this Morita equivalence is what it's known as a stack. So this is what a C-infinity stack is. This is what a stack is. And our quantum toric stacks will be stacks as well as non-commutative spaces. Now, given a manifold, if I give you two atlas, I can give you two groupoids. The good thing is that the two groupoids are Morita equivalent, homotopy equivalent, Morita equivalent groupoids. And so a manifold is the Morita equivalent class of the groupoid associated to its atlas. So the Morita equivalence class of groupoids generalizes equivalence of atlases for manifolds. But now I can take group actions, for example. And if I did it with group actions, say for finite groups, for example, they still are groupoids, as I explained. Now I would get that orbifold atlases also fall into this formalism, for example, and many other things. So this is a generalization of the concept of atlas and equivalence of atlas. And this gives me stacks. Stacks are geometric objects that generalize manifolds and are more like orbifolds than like manifolds. In any case, foliations give me, what are foliations? Well, foliations are manifolds that are divided into the joint union of other manifolds of the same dimension. For example, this is a big manifold divided into all these leaves of the foliation. And you have an atlas of the original manifold that is horizontally foliated, and the change of coordinates preserve the foliation, the leaves of the foliation. And this is, and when you do a global atlas, you get a global foliation. For example, here you have a foliation. You get this cylinder, you get all these paraboloids, and they divide the interior of the cylinder into submanifolds. And then outside, you get these other shapes. In any case, if you take any point here and you draw a little small cubic box, it will look like this. And so this is a foliation. And so, well, foliations, interestingly so, foliations really are called foliations also in geology. And these are a foliation in geology. In any case, if you have a foliation, you can produce canonically. Well, the groupoid that you produce is not canonic, but it's Morita equivalence class. It's homotopy equivalence class of the groupoid that you obtain from this, the holonomy of the foliation. It's a well-defined object. So every foliation gets associated a well-defined C-infinity stack. So you get a smooth stack in the C-infinity category for every foliation. And I'm going to use these stacks very much. So to every foliation, I will associate stack. Okay, So again, I recommend that book for details on this construction. I have to take a transversal to make it a tal group. The groupoid is not canonical, and the original holonomy groupoid could be the original groupoid could be large, but then if I take transversals and I do the holonomy, I can ensure that this is an étal groupoid, and then I can make sure that there is this canonical stack associated to the foliation. In any case, to every such étal groupoid, you get associated finally a non-commutative algebra. You can think that this algebra has a nice representation of operators if you feel more relaxed at heart by thinking of them as operators. But in any case, it can be represented also as functions on the space of arrows. And if you have a groupoid, you associate its convolution algebra to the groupoid. Just like to a Lie group or to a finite group. To a finite group, you associate its group algebra. To a Lie group, you associate its convolution algebra. And to a Lie groupoid, you associate its convolution algebra, and it's a non-commutative algebra, just like for a Lie group. And it's an algebra, and it's non-commutative. And this algebra is the non-commutative algebra that we will associate to a stack, to a Lie groupoid, to a foliation, for example. To a foliation, I can associate a Lie groupoid. To a Lie groupoid, I can associate an algebra. So to a foliation, I can associate an algebra. And now the thing. Now, if it was a discrete group, a finite group, you would get exactly the group algebra. If it is the Heisenberg groupoid, you get the matrix algebra that Max Born introduced into the paper of Heisenberg. So Heisenberg only had the non-commutative objects, and it was an intimation, and they didn't have the language. But then Max Born said, relax, they are matrices, so it's okay. Now we would be very relaxed with using non-commutative letters or symbols, but not at the time. Anyway, to any groupoid, I can associate its convolution algebra. And this gives me a Gelfand duality. Something happened to my screen. Problems. Here I am. So I have this, Gelfand duality. The categories spaces of Hardow compact topological spaces is the same as the category of commutative algebras. They are the same category. It's the same thing. I asked earlier on, what is a space? And I answer now, space is a commutative algebra. Given a topological space, its corresponding algebra is the algebra of continuous complex valued functions on X. With pointwise multiplication, it's commutative. And of course, there is this is a contravariant equivalence in the sense that it inverts a mapping of spaces gives me the opposite arrow of algebras. In classical geometry, one starts with an affine variety and produces a commutative algebra by taking its regular functions. Then one can go back to X by taking the spectrum of maximal ideas. And a similar but more delicate construction works in the case of any Hausdorff compact topological space. It works for Hausdorff compact topology, and even more generally, and for manifolds you can add Fréchet structures, etc., etc. In any case, this is called Gelfand duality. And this is very important for us. So this is Gelfand duality. And, what are non-commutative spaces? Definition. The category of non-commutative spaces is the opposite to the category of non-commutative algebras. Up to this Morita equivalence that I have not spoken about carefully today. And I will not, but you have to put it there. So it's not exactly algebras, it's algebras up to this Morita equivalence, but it's okay. So this definition is designed to extend Gelfand duality into the non-commutative realm. So just as a space is the same as a commutative algebra, a non-commutative space is the same as a non-commutative algebra. And just add the convolution functor from groupoids to non-commutative algebras descends to the convolution functor from stacks to non-commutative spaces. In other words, if I take a stack, I can take any atlas, any groupoid that represents it. Then I can take the convolution, I get a non-commutative algebra, and its Morita equivalence class is a non-commutative space. And this is a well-defined map from stacks to non-commutative spaces. This is a good convolution map from stacks to non-commutative spaces. So if I give you a stack, one of these stacks that I mentioned, then applying the convolution functor, you get a non-commutative space. And this is the relation between stacks and non-commutative spaces. And these non-commutative spaces, algebras, can be represented in every case that I will speak of as operator algebras, as algebras of operators in Hilbert space. So, so that's a non-commutative space. And here I reach more or less half of the talk, and they asked me to make a pause. So any questions?
I had asked participants to send questions via the chat, but I don't see any. I have a little question, namely, in the C, the convolution algebra, you do not care whether, I mean, they are just functions.
Yeah, well, you have
Are
to
they
do some...
finitely supported? Are they, you know, you complete the algebra in some sense?
Yeah, of course, yes. I have to be careful with that. I have to be using these C-star algebras. I was careful enough to make the situation convergent by taking et al, so that this sum makes sense. But yes, I have to do this kind of procedures that you describe. I'm not going into all these technical details today, but one has to be...
I just meant, I mean, if you really are interested in the algebraic, strictly algebraic.
Yeah, the C-star algebra associated to the groupoid.
And the C-star algebra. Okay.
Right. Okay. The C-star algebra. Otherwise, well, I would have too little information. I need a little bit more.
Okay. Sorry, are there any more questions?
Perfect.
Okay.
So this is Gelfand duality. And well, it's perhaps better to make to write an explicit example of a non-commutative space that is a quantum torus. This is the most basic example of a non-commutative space. The quantum torus corresponds under Gelfand, non-commutative Gelfand duality, to this algebra, the algebra that has two periodic generators, x and y, but they don't, rather than commuting, like they would commute in the usual torus, x and y would be the horizontal and vertical coordinates of the torus. They don't quite commute. There's this very tiny little number that that makes this, well, very close to zero, so that makes this very close to one. So they almost commute, they don't quite commute. And this relation is precisely the Weil exponential form of the commutation relation appearing in the work of Heisenberg, Born, and Jordan. And the algebra AH, on the other hand, is, and this is very curious, only truly non-commutative when H bar is irrational. Yeah. When H bar is rational, although it's non-commutative, of course, it's Morita equivalent to a commutative algebra. So only when H bar is irrational, this algebra is truly non-commutative. It really comes from non-commutative geometry. So this is the algebra, the non-commutative space, called the quantum torus. And well, it is a theorem of Kohn and Riffel that you can classify these quantum tori, these algebras, up to Morita equivalence, by an action of SL to Z. So this already was understood in the comprehend note. And so you have all these, but you have still many quantum tori, many of them. And this is SL to Z relation between the algebras hints at a possible geometric interpretation for this algebra. So far, it's just an algebra, but maybe there is a foliation that gives me this algebra. Is there a foliation that gives me this algebra? And it's a beautiful insight of Alan Kohn that there is. And it is the Kronecker foliation. The Kronecker foliation, it's a beautiful discovery of Alan Kohn, that the non-commutative torus can be thought as the non-commutative space given by convolution that models the space of leaps of the Kronecker foliation. The universal covering of the classical torus is the Euclidean plane. By taking the foliation of all lines of slope h bar on the plane and projecting it into the torus by the covering map, we obtain the Kronecker foliation of a slope h bar on T2. And by taking a vertical transversal circle to the foliation, let's draw it. By taking a vertical transversal circle to the foliation, it is easy to see that the holonomic groupoid, that is the error when you come back through one of the leaves of the foliation in this transversal, this error, the set of these errors is the holonomic groupoid of this foliation is S1 modulo a rotation by h bar on this transversal circle, where rho h bar acts on S1 by a rotation of angle h bar. It can be shown that the convolution algebra is a h bar using Fourier series, and it's a fun exercise. In any case, this is the Kronecker foliation, and its holonomy, this error of coming when you come back through the leaf. And well, this is h bar. H bar is this small error here when you come back. And there's this dichotomy: when Q is rational, these things close into torus knots, and when this thing is irrational, well, these things don't close into torus knots. They go on and on and on, and every leaf of the foliation is dense in T2. So there's two cases. If h bar is rational, the quotient is a circle by the R action of this dynamical system. And when h bar is irrational, the quotient is non-Hausdorff, it's no longer a manifold, no, it's a non-Hausdorff topological space that is better modeled by a stack. So, or a non-commutative space. So anyway, so let me shift gears now dramatically. So far, that was my crash course on non-commutative geometry, that's it. Of course, there's infinitely more to say. And now let me give you a crash course on toric geometry, of 3-minute crash course on toric geometry. And then I will have to marry these two theories and then get non-commutative toric geometry, quantum toric geometry. So this is the archetypical example of a toric manifold. So this is the Riemann sphere, and this is the moment map. The moment map is just the horizontal map that projects the sphere into a closed interval with the north pole in the maximum of the interval and the south pole in the minimum of the interval. The inverse image of a point in the interval is a circle S1, a circle of dimension 1 via the moment map. And this is the Riemann sphere. This is its moment map. Is the same as rotating the sphere. This circle action meant to be a circle action on the sphere, rotating the sphere and taking the quotient by this rotation. And then you get this interval. And this is the moment map. And now notice that the Riemann sphere is the compactification. If you take 2 points off the Riemann sphere, you get the same by stereographic projection as the complex plane minus a point. And this is called the one-dimensional complex torus, C star. the complex plane minus a point minus a zero. C star is the one-dimensional complex torus. C star cross C star is a two-dimensional complex torus. Is the complexification of the real torus, just in the sense of complexification of Lie groups. So C star, you are to think of it as a thickened circle, a complex thickened circle. There is a real circle inside, and then there is a complex plane minus the point. The circle is inside, and this is the C star, the one-dimensional complex torus, and so on, two-dimensional complex torus. So a general toric variety is some compactification, equivariant compactification. These rotations extend to the whole complex manifold. It's a complex manifold, a toric variety. Think of it as compact today. It's a compact complex manifold where this circle, well, now it's a real torus that is acting on this manifold. And it's actually more than complex, it's scalar. It has a scalar metric, it has a symplectic form. This action is Hamiltonian, and then you can think of the moment map for the toric variety in general. That is this compactification of the complex torus. So you have the complex torus C star cross C star cross C star cross C star. You have this compactification of the complex torus, but you have many compactifications of this complex torus, unlike the one-dimensional complex torus that admits only one compactification, the Riemann sphere, that is equivariant with respect to these actions, and etc., etc. These compactifications where the action of this torus extends holomorphically, now there is many of them in higher dimensions. For example, two compactifications of the two-dimensional torus are P1 cross P1 on the one hand, and P2 on the other hand. There are two different compactifications of C star cross C star. And of course, there is many more. How many more? Well, as many as these funds. There's a combinatorial geometric structure that enumerates how you can do these compactifications, and it's many of them. Now, the question that we want to solve is how to define a meaningful modular space of these manifolds. Unfortunately, or fortunately, or whatever, as toric manifolds, not as complex manifolds, as toric manifolds with these equivariant actions and everything, all the structure, they are rigid. You cannot deform them as toric manifolds. But you can. So we're going to produce a nice modular space for these toric manifolds. Again, this is the moment map in the more general situation of a toric variety. Now this is your, fancifully, this is your toric variety. And this is the fun. This structure here, this subdivision of R2 into cells of dimension 2, and then cells of dimension 1, and then one cell of dimension 0. This stratification of R2 is called a fan, made of these rays and these faces here. The dual of this fan is this polytope. Well, it's not the dual fan, but a dual object to this fan is this polytope in Rn, and in the Kähler case, the moment map that can be defined using the symplectic form and the Hamiltonian action of the torus, well, gives you this segment, this line segment, is like the line segment for the Riemann sphere. So you get here a Riemann sphere that is smooth and just, well, the drawing is not topological only, not geometric. And you get the inverse image of this point is this real torus, and so on and so forth. It has this structure, the moment map. And so the inverse image of every point is a torus of dimension 1, a torus of dimension 2, a torus of dimension 0. These 5 rays in a stratified manner, this toric manifold into this combinatorial geometric object, this rational polytope, slopes are rational. The slopes are rational. And the inverse image of every point is some sort of torus. And these are the classical story. And now I have to do the quantum story. So what I'm going to do is I'm going to replace all this tori by quantum tori. So in our paper, classical Toric geometry is generalized by replacing all the classical tori in Toric geometry for non-commutative tori. And one can obtain non-commutative toric varieties, or quantum toric varieties is the same thing. Quantum toric stacks are the stack, and non-commutative toric variety is a non-commutative space associated to the stack by the convolution. But you can ignore the difference and say it's the same thing. Now, the possibly irrational, now fans in the classical theory, fans, these are compositions of the plane into this cone strata, this cone, 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 this, the composition into cones was rational. All these slopes were rational. And this is why you can't deform toric varieties, because they are rational, and then you cannot move to the next one because they are rational. But now, if you replace by quantum tori, you can deal with irrational fans, irrational polytopes, and they don't live in Qn or in Zn, like in the classical theory, but they live in something called a quantum lattice. Some people call this a quasi-lattice. We call them a quantum lattice. A quantum lattice is a finitely generated, possibly dense abelian subgroup of Rn, as it may have more than n generators over Z. Think, for example, of the lattice in R, in R1, generated by 1 and the square root of 2. It has two generators in R1, 1 and square root of 2. And when you generate every possible rational combination of 1 and the square root of 2, you get a dense quantum lattice inside of R. So that's what it could look dense in Rn, because it could have many generators, more than Rn, more than n, etc. Anyway, a quantum fan, this is not meant to be 3D. This is meant to be 2D. This is a cone, this is a cone, this is a cone, a cone, a cone, a cone, a cone. This is a stratification, it's a fan. It's a classical fan, but now it may be irrational. Now this slope may be irrational, or this may be irrational. And it's very similar to a classical fan in Toric geometry, but instead of an integral lattice, it is equipped with a quantum lattice. And we mark some points here. We do some mark points, just like in the theory of modular spaces of Riemann surfaces, you mark points to get a good modular space. We mark points to get a good modular space. So this is a quantum fan. And well, our theorem says, one of our theorems says that the category of quantum stack, or quantum toric stacks, or quantum toric, or irrational toric varieties, or non-commutative toric varieties, or whatever you want to call them, is equivalent to the category of quantum fans with preserving these structures, of course. So now you have a way to, there is this theorem, is proved in the long paper, and now you have this theorem, and now you can work with these fans and try to produce a reasonable modular space out of these things. And let me look at my time. In any case, then a modular space of toric varieties can be defined. We fix the combinatorics of the polytope of the fan, and this is analog in the classical theory of modular spaces of Riemann surfaces to fixing the genus. In fact, we should call the combinatorics of the fan associated to a toric variety its genus in our world. You know, we fix that discrete data. We fix that. And then in a large family of favorable cases, the modular space is a complex orifice. So its rational points are precisely the classical toric varieties. So now we produce a nice modular space, but you couldn't form classical toric varieties. But if you add the non-commutative ones, the quantum ones, you can. and it's almost all of them, because the rational points are the classical ones, and every other point in the modular space is a quantum toric variety. Its irrational points are precisely the truly non-commutative toric varieties. And non-commutative geometry is precisely what is needed to define a nice modular space of toric varieties. What we do we define these modular spaces, and we start the study of their topology and that kind of thing. But in the long paper, we do not compactify these modular spaces. In the long paper, we do not compactify these modular spaces. And so there is a technical condition that we add and whatnot, but the result that I announced today, and is the result that I will send to the journal, to the Argentinian journal, is in collaboration with Katzarkov, Meersseman, Meersseman, this should be a Meersseman, not Laurent, and Verjovsky, for the whatever call, for a certain nice, especially nice case of calibrate mark points, all these things, you put all the bells and whistles in the right place. The modular space of quantum projective spaces, with all the markings, and everything to make it as nice as possible, then is exactly the same as tropical projective spaces. The compactification. So we can compactify this modular space. And when we compactify this modular space, we get exactly at the way the toric, quantum toric stacks, commutative or not, are degenerating into other quantum toric stacks, commutative or not, as you deform them, compactifies the space, just very much like in the classical case of the compactification of curves, a stable curve compactification by Kontsevich. And you get this modular space, and this compactification carries a natural tropical structure. It's very amusing. And it is exactly tropical projective space of dimension n. It is exactly tropical projective space of dimension n. So I'm going to stop here to ask if there is any questions. Yes.
Yeah, I have one.
Yeah.
So do you consider what would be analogs of affine varieties?
Yeah. We can do a.
I mean, are they comodular algebras over
Are they what?
non-commutative tori? Comodular algebras over non-commutative tori, just as I mean, monoid, the affine toric varieties, have a coaction of a tori, of a Laurent polynomial ring.
Yeah, yes, it's very close to that. But the way we do it is the following. To every one of these objects, to every one of these quantum toric stacks, what we do is we use some very nice distinguished atlas coming from something called Lbm Theory. So these are very funny holomorphic foliations on complex manifolds that are not symplectic, that generalize Calabi-Ekman vibrations. So these are these irrational foliations on these compact complex. But if you restrict to cones, there is no problem. And so you can define everything for cones and non-complete fans. And you have these foliations, and you have the associated non-commutative spaces. And indeed, because we can produce a geometric action of the Kronecker foliation at the geometric level on the foliation, on the holomorphic foliation on these complex, not symplectic manifolds, not Kähler, then of course when you pass through convolution, you will get these coactions of quantum tori on the non-commutative spaces, and the equivalence statement of it being dense in the whole space. So yes, you have everything, but I have to say that one of my students is writing down explicitly the sister algebras and all this story that we don't write explicitly. We know they exist, and we know everything acts well, and we know everything because of the geometric picture. But it is worthwhile writing the explicit sister algebras and the Morita equivalences and the actions to define it purely in terms of sister algebras. The problem with the sister algebra approach for what we want to develop is that the modular space would be a little bit mysterious, because we want this modular space is the right modular space in terms of the Kodaira-Spencer deformation theory for stacks developed by Laurent Meersseman. It's really the Kodaira-Spencer in the holomorphic sense, the right modular space. And for the sister algebras, it's not so clear what scalar or symplectic or this should be. Probably there is ways to say it, but we haven't said it in the language of sister algebras, all that story. And so this is something to develop. In fact, nearly everything is to develop. This is just that's why the paper is called Foundations. It's just the foundational paper of the theory. Any other question?
If I may ask a question that's perhaps not well defined. So your result that you're presenting here says that the moduli space of quantum projector spaces is tropical projector space of dimension n. So can you consider quantum projector space with some additional structure, whatever additional structure means, and look at their moduli space and perhaps get other tropical algebraic varieties?
Absolutely. In fact, this is only the kind of the most simple case. Many things are happening at the same time. Antoine Voava, student of Laurent Meersseman, has developed the case of the non-simplicial case and the general simplicial case. We just did projective space, but he has developed the general, and so he has compactified inside some tropical Grassmannians, and so the modular space ends up being some tropical manifold inside some tropical Grassmannian. And so there is many of them, and it's a whole zoo. It's a whole zoo. And all my modular spaces, in the case of projective space, they form, of course, a simplicial object in the category of tropical manifolds. So they form, of course, a simplicial object in the category of tropical manifolds. And this intimates that something much simpler, perhaps. I mean, there is, of course, these very subtle Mirzakhani results and etc. But something like topological recursion should happen here for all these families of tropical manifolds that represent modular spaces of these toric quantum toric stacks and quantum non-commutative spaces. Any other questions?
One more thing. In the classical setting, well, the affine toric varieties are monoid algebras of certain particularly nice monoids. And monoids are the affine varieties over the field with one element.
That's right. That's right.
So, is there any relation with this geometry over the field with one element of con?
Yeah. The classical case, of course, you have this very natural structure over the field of one element for toric varieties. Here, I should say that what happens here is that you just need a good notion of exponential function. it's very important for these variety. These are transcendental objects as we have defined them. But of course, depending on the flavor of your geometry on one element, you are talking about algebraic geometry over the field of one element. But you could also develop, and we have some ideas also of how to do this. I mean, the basic idea, we know how to do it. Some transcendental geometry over the field of one element, not algebraic, to incorporate this exponential mapping that is this winding map. If you incorporate this mapping into your allowed mappings in the geometry over the field of one element, and you can, then these are these also transcendental objects over the field of one element. But of course, now you have you have to incorporate these quantum lattices as your monoids, rather than just so you have to somehow remember this closeness of these elements, and then a Verjovsky formalism is more appropriate for this task. But as I said, everything is to be done.
Okay, so are there any more questions? Because we don't have much time. At 4, the sessions are starting. So if not, we thank the speaker.
Thank you very much. It was an honor, and see you in the next talk.
Okay.
Bye-bye.
Bye-bye. Uh-huh.